My name is Amit Singh Bhati, and in this video I will be explaining our work titled Nonce-Misuse Security of the SAEF Authenticated Encryption Mode. This is a joint work with Elena Andreeva and Damian Vizár. Since SAEF is a fork cipher mode, let us start by understanding what the fork cipher is and how its security is defined. Fork cipher was introduced in SAEF 2019 by Andreeva et al. And is one of the second round candidate of the NIST lightweight cryptography. A fork cipher is a symmetric key primitive which takes two inputs, a t-bit tweak and an n-bit plaintext input, and it returns two n-bit ciphertext blocks as output. The security of the fork cipher is defined by indistinguishability from a pair of random permutations under chosen ciphertext attack. The notion is denoted by pseudo-random tweakable fork permutation, also known as PRTFP. SAEF is defined as one of the two fork AE candidates, which are selected as one of the candidates for the second round of the NIST lightweight cryptography. Unlike to its sibling PEF, SAEF is a sequential mode and it's online AEAD, hence it minimizes the memory footprint and is more useful for the most constrained devices. In the original paper of fork AE, SAEF was proven AE secure against nonce-respecting adversaries. However, in most use cases of lightweight cryptography, nonce-reuse presents a very realistic attack vector. You can see here the bounds that were presented in the original paper. In our work, we have investigated the provable security of SAEF when the nonces are allowed to repeat under the refined version of OAE notion given by Fleischmann et al. We have shown that SAEF is OAE secure with no modification in the scheme. Further, we have also shown that the integrity remains undamaged with nonce reuse, whereas the confidentiality degrades by a very small factor. OAE security by Fleischmann et al. Is derived from online ciphers. Online ciphers were introduced by Belgium et al. In 2001. An online cipher is a length preserving function which takes a sequence of n-bit plaintext blocks as input and returns another sequence of n-bit ciphertext blocks with equal number of blocks. The security of an online cipher is defined by indistinguishability from a random online permutation. An online permutation, as you can see here, is defined as a length preserving permutation which also preserves the length of the blockwise prefix. That is, if two input sequences of online permutation shares exactly x many blocks as prefix, then their corresponding output sequences will also contain exactly x many blocks as common prefix. In other words, ith output block of an online permutation is dependent on the ith input block as well as all input blocks processed before that. In expression, you can see here that Ci is defined as. In this slide, I will recall the OAE security and its refined version for messages with incomplete last blocks. Let us consider that EK is an online AEAD scheme which takes a nonce N, associated data A and a plaintext M as input and returns a ciphertext C and a tag T as outputs, where tag T is of tau bits. Informally, we say EK is OAE secure if the ciphertext outputs of EK looks like an image of an online permutation for every input tuple of NAM, whereas the tag outputs looks like random strings. For the formal security description, we use the two requirement flavor of this OAE notion, separating confidentiality and authenticity. Confidentiality is defined by indistinguishability from a random online permutation concatenated with a random function, whereas authenticity is defined here by unforgeability. Further, to deal with messages that are not N-aligned and contain incomplete last blocks, we use the refined notion of Huang et al. by expanding the output length of the random function by the length of the last incomplete block. This dedicated slide presents the formal definition of the longest common prefix. As the name suggests and I described earlier, longest common prefix between two queries is defined by the maximum number of blocks they share as prefix. For example, if two queries contain same nonces and same values of A1 but different values of A2, then the longest common prefix of those two queries will be 1. Also, the second result here is another way of interpreting that pi as an online permutation preserves the length of blockwise prefix. With this slide, we now know the basics that will be required to understand the OAE security analysis of SAEF mode. Let us now proceed with the main proofs. We have used Patarin's coefficient H technique as the main tool for our security proofs. Let us quickly recall the coefficient H technique from this slide. This technique is used to prove indistinguishability of a real system R from another ideal system I with an information theoretic adversary using the concept of transcripts. A transcript, as shown here, is defined as a complete record of the interaction of an adversary A with its oracle in this indistinguishability experiment. For example, if mi zis are the input and output of the ith query of A to its oracle over a total of q queries, then the corresponding transcript is defined as a tuple containing all these q pairs of mi's and zi's. The task given to A here is to distinguish the real world R from the ideal world I. Let dz denote the distribution of transcripts in the world Z, and big tau is the set of all attainable transcripts. A transcript is said to be attainable if the probability of achieving the transcript in the ideal world is non-zero. Let's also consider a partition of the set tau into tau good and tau bad. Then the main result of the coefficient H says if there exists an epsilon with this probability ratio of transcript distribution lower bounded by 1 minus epsilon for all good transcripts, then the advantage of the adversary of distinguishing R from I is upper bounded by epsilon plus the probability of ideal transcripts being bad. Coming to the main proofs, let us denote the masks which are processed internally here as deltas. We will be using these deltas for the proofs. Now for authenticity of SAEF, we can redefine the notion as follows. Here A is given an access to both encryption and decryption oracles. In real world, both of these oracles are faithfully implemented as in SAEF, whereas in the ideal world only the encryption oracle is implemented correctly as it is in SAEF. However, the decryption oracle is replaced by this function which always returns invalid for all types of decryption queries. Note that in the real world also the decryption oracle can return invalid as an output if the fed ciphertext does not verify its tag. However, in the ideal world it will always return invalid. One can easily show a bijection from this notion of indistinguishability to the notion of unforgeability. Informally, we say that if an adversary can distinguish these two systems, then she can also forge a valid ciphertext, and vice versa. In addition to the oracle access, we also provide the internal mask, that is deltas and delta bars, to the adversary, but only in the end of the interaction, so that the adversary cannot influence its queries using these delta values. We extend the transcripts by adding these deltas and delta bar values. So here deltas are the internal mask defined for the encryption oracle and delta bars for the decryption oracle. Clearly in the real world, deltas are defined using SAEF and thus can be considered as an output of a random permutation, whereas in the ideal world, specifically for the decryption oracle, these deltas are not defined and thus are chosen uniformly at random. Now consider a transcript which contain all distinct values of inputs and deltas. Then we know that the probability of achieving that particular transcript in the real world is higher than in the ideal world. This is because in the real world, all these deltas, including the delta bars, are defined using permutations, and thus the randomness here depletes as we process more and more queries, whereas in the ideal world, all these delta bars are independently chosen at random and remains equiprobable. With this, we get the following inequality and this ratio, which gives epsilon equal to 0. To give an example that why the same argument doesn't work out of this set of good transcripts where we have collisions, let's consider a transcript which contains two different values of delta 1 and A2 such that the inputs of these four permutations are different, but the outputs delta 2 are same. That is, the transcript contains a mass collision for delta 2. Clearly, in that case, the probability that this transcript can be achieved in the real world is 0 because no permutation can give same output for two different inputs, but the same can be achieved with non-zero probability in ideal world. Although we get a value of epsilon by doing an informal analysis using the good transcripts, one still needs to carefully define all the bad cases and define bad transcript using those bad cases, and then we say that the transcript which is not bad is good, and this analysis follows. Let's describe the bad events and the bad transcripts. Let us color code these forked permutations on the basis of the fat tweaks. Different colored permutations are independent of each other. Excluding the common prefixes, we say a transcript contains input collisions if there exist two forked queries with same tweaks and same inputs. This is a bad case as the output of such fork call will always be same in the real world, and the next mask will have no randomness. We reformulate deltas and delta bars as a common sequence of deltas, where the ith query is ordered by first the encryption queries and then the decryption queries. And after the longer common prefix, all the deltas are chosen at random in the ideal world. Talking about the probability of such input collisions, if xji and xj'(i') are the first input blocks after the longest common prefix, then we will have delta ji equal to delta ji', but the xji and xj'(i') will not be equal. Hence the probability of this collision will be 0. However, in all the other cases, these deltas will be fresh and uniformly chosen, and thus this collision will have a probability of 1/2 to the n. Since there are total sigma many such fork calls in a complete session, there are sigma choose 2 such pairs of fork calls, and thus the total probability of such collisions in ideal world will be sigma²/2 to the n+1. The second bad event is the mask collisions. It's the case when the inputs are different with the same tweak, but the corresponding output masks are the same. Clearly, such an event cannot occur in the real world, but this can occur in the ideal world. In the ideal world, when the inputs are different, it is clear that the corresponding deltas are not in the longest common prefix, and thus they are uniformly distributed. In that case, the probability of such collision is 1/2 to the n. And since there are total sigma many fork calls, we have sigma²/2 many such fork call pairs which can have such collisions, which gives the total probability of mass collisions at sigma²/2 to the n+1. The third and final bad event is the forgery attempts, when a tag provided in the decryption query verifies its corresponding ciphertext. That is, when this equality holds for its last fork call of that query. There are 3 cases for such collisions to occur. First, when with the previous encryption query, this decryption query shares the longest common prefix up to the last block, including the last block. In that case, the delta and the input blocks are fixed and same as the old encryption queries. However, the tags are different. So in that case, this collision has a probability of 0. The second case is when with the previous encryption query, this decryption query sets the longest common prefix up to the last block, excluding the last block. So in that case, again the deltas are fixed and same as the old encryption queries, but the last block X are different, which gives the probability of this collision as 1/2 to the n. And this probability degrades as more and more queries are made with the same fork call, because a fork cipher is a permutation. In worst case, this probability degrades to 1/2 to the n minus QE, which is upper bounded by 2/2 to the n, assuming total number of encryption queries are upper bounded by 2 to the power n minus 1. And the third case is when this delta in the decryption query is not generated using the longest common prefix of any previous encryption query, and hence is uniformly distributed, which again gives the probability of this collision as 1/2 to the n. Since there are total QV many verification queries, the total probability of such collisions will be QV/2 to the n. This is an approximation, as including all corner cases and the degradation of permutation, we get the exact bound as 4QV/2 to the n. If none of the bad events occur, we get fresh and distinct delta masks and fresh randomness for the last ciphertext block and the tag. The probability of idle transcripts being bad, that is, when one of these bad events are said to be true, is upper bounded by the union of these probabilities. With this inequality and epsilon equal to 0, we get the proposed bound of authenticity for SAEF. With similar arguments, we can now define the confidentiality proof of SAEF. Here, the adversary is given an access to the encryption oracle. In the real world, the encryption oracle is implemented as in SAEF, but in the ideal world, the encryption oracle is replaced by an online permutation concatenated with a random function. Similarly, deltas in the real world are defined using SAEF, whereas in the ideal world, they are not defined and thus chosen uniformly at random. These internal deltas are provided to the adversary, but only in the end of this interaction. We extend transcripts again here by adding these delta values. Just like the authenticity case, in ideal world here also the deltas are uniformly distributed, whereas in the real world they are generated using permutation, and with that we get the following inequality for all transcripts which are good, that is, where all inputs, outputs and deltas are unique. With this we get epsilon as 0. Talking about the analysis of bad events, we have two bad events. The first bad event is input collision, just like the authenticity, when the tweaks and the corresponding inputs are same for two different fork calls modulo their longest common prefix. Again, in the ideal world, this delta ji and delta j prime I prime can be fixed and same if they are generated under the longest common prefix, or otherwise they are uniformly chosen at random. In the first case, when they are same and they are defined under the longest common prefix, the corresponding values of xji and xj prime I prime will be different to fulfill the definition of longest common prefix, and thus the probability that this equality holds will be 0. However, in the other case, when deltas are uniformly chosen at random, the probability that this equality holds is 1/2 to the n. Since there are total sigma many fork calls, that is sigma square by 2 many fork call pairs, we get the total probability of these input collisions as upper bounded by sigma square upon 2 to the n plus 1. Second bad event is output collisions, when the inputs are different with the same tweak, but their corresponding outputs in either of the fork output are same. Unlike to the authenticity case, these left output collisions are valid bad events now, because the encryption outputs are not generated same in the both worlds. In the ideal world, the encryption outputs are generated using an online permutation, which means such output collisions needs to be taken care of separately. Talking about the collision probability, there are two cases. First case is when the delta ji and delta j prime I prime are defined under the longest common prefix. which means they are fixed and same, but xj I and xj prime I prime are different. In that case, the inputs are not colliding, but since xj I and xj prime I prime are different, in the ideal world, with an online permutation, the corresponding yj I and yj prime I prime will also be different, which means there is no collision in the left output of the fork permutation. However, on the right output, delta j plus 1 I and delta j prime plus 1 I prime can collide because they are uniformly distributed and they are not under the longest common prefix. In the second case, when delta j I and delta j prime I prime are not under the longest common prefix and not fixed, which means they are uniformly chosen at random, and if the inputs are different, the outputs can collide in both of the outputs of the fork call, and thus yields a probability of collision as 2 upon 2 to the n. Since there are total sigma many fork calls, which gives sigma square by 2 many fork call pairs, we get total probability of such collisions as upper bounded by 2 sigma square upon 2 to the n plus 1. If none of these bandwidths occur, we get fresh and distinct outputs, and with total probability, we get the probability of ideal transcripts being bad, upper bounded by 3 sigma square upon 2 to the n plus 1. Further, with epsilon equal to 0, we get the proposed bound for the confidentiality of SAEF. We have showed that SAEF is secure under nonce-misuse with maintaining the same integrity level, whereas the confidentiality is degraded by a very small factor. With the relation between online misuse resistant AE schemes and blockwise model attacks as presented by Vizár et al. In FSC 2017, we conclude that SAEF is safe to use for blockwise processing, which can be very useful for constrained devices with limited memories. An interesting avenue for future work is investigating the security of SAEF under the release of unverified plaintext ROOP security. ROOP security is also a natural target in the use cases for lightweight cryptography, where the similar constraints are applied. Our conjecture is that SAEF is inter-ROOP secure without any modification. With this, I end the presentation. I hope you liked the video. Thank you.